Good morning, good afternoon, good evening, good wherever you are, and welcome to this SNIA presentation, today presented jointly by the Cloud Storage Initiative of SNIA and the entertainingly named SSSI, or the Solid State Storage Initiative. Today we're going to be doing a webcast about containers, containerization, and persistent memory. This is a new technology we want to discuss with you and to let you know what technical advances we're beginning to see in the area of persistent memory and how that applies to containers and the use of containers in a modern data center environment. So without further ado, here's the legal parts. Basically this says anything you use out of this, we'd be really grateful if you recognize our copyright and use the slides in their entirety. And the slides will be available after the presentation. I'll make sure that there's a link that you can get at the back end to get a copy of the slides. And secondly, that if anything you use out of these slides causes you grievous bodily harm, or a leg falls off, or things just stop working where you are, okay, don't blame the presentation. There's no liability, there's no warranty with this. Legal boilerplate, usual stuff. So today, I'm on the far right, I'm Alex McDonald from NetApp, and I'm the chair of this session today. And we're joined by three experts in this area. The first is Chad Thibodeau of Veritas. Morning, Chad.
Good morning, Alex.
I think it's morning where you are, Chad. And we're also joined by Arthur Sainio of Smart Modular. Morning, Arthur.
Hello, Alex.
Mark Carlson of Toshiba. Morning, Mark.
Hello, Alex.
And it's afternoon where I am. And it may be some different time of the day where you are. So, without further ado, just a quick SNIA at a glance. What is SNIA about? There are 160 unique member companies in the Storage Networking Industry Association, to give us a full title. We've got about 2,500 contributing members and about 50,000 IT end users and storage pros worldwide that follow us. The organization, and I would recommend you go and look at the website for more details. We just recently updated the website. You can find more details of the organization at snia.org. Okay, so today's agenda is we're going to talk about three things. First of all, we're going to talk about persistent storage for containers and what that actually means in terms of storage requirements for containers and in essence, talk about persistent storage rather than the transitory storage that we sometimes use for containers. Secondly, we're then going to talk about persistent memory for containers. This is a new technology. This is not your father or your grandfather's storage. It is very modern concept of using memory, persistent memory, for storage of data, and in particular how that relates to containers. And then lastly, we're going to talk about the kind of software changes that are already in place and that need to be made for persistent memory-based containers. So it's a fairly complex topic, and we're going to be taking quite a lot of material and expanding out on it. And if you want more information, there's some really good information on the SNIA website, on the SSSI pages in particular, that talk about persistent memory. And again, I'll give you the links at the back end of this. Before we just start in the presentation, just let me remind you, you can ask questions. There's a question button there. So if there's something you want to find out from our speakers today, please just pop a question and I'll make sure it gets asked if we've got the time. And secondly, as you leave the presentation, there's a ratings button. If you could rate this from 1, which is, goodness, I should have been doing something else, that was a complete waste of my time, all the way up to 5, which is, I really like this, we need more of this. And you can also give us a comment and let us know how we're doing. So without further ado, I'm going to hand you over to Chad Thibodeau, who's going to talk to you about persistent storage for containers. Chad.
Sounds good. Thanks, Alex. So what I'd like to do is to start by setting the stage. The software-defined storage market, or software-defined storage in general, is really what we are seeing is being used to provide the storage services for containerized applications. So whereas traditional storage often is used for more traditional applications such as Oracle, or it could be Exchange, etc., what we're seeing is that if you look at the ecosystem of storage providers supporting containers, what we're seeing is that they are all software-defined. And a lot of that goes towards the benefits of why users are deploying containers, which is they are much more portable, they're platform agnostic, and they are much faster to start up and tear down. So if we just take a quick glance, the chart on the left basically is showing really a decline in kind of traditional enterprise storage. So you could assume that to be, again, SAN, NAS, and then let's say traditional DAS. And then if you look at the section of blue, kind of in the middle of that chart, you have enterprise server storage, SAN storage, which is growing. And then what's interesting to me, the most interesting, is really the green, which is the hyperscale server SAN storage. So what you're seeing with that is, again, the kind of migration or movement from more traditional storage methods to a scale out, so hyperscale referring really to a scale out type of an architecture. And again, that really lends itself to the value proposition and benefits of utilizing containers in deploying applications. What you see with those bubbles is basically just showing the trajectory of the software-defined storage market and how it's growing, pretty substantially from 2017 at around $7 billion to $22 billion for 2020. So just wanted to provide a little bit of kind of market stats. If we dig a little bit deeper now into containers and look at the container landscape, there's some interesting statistics that you see on the slide. And by the way, this is a snapshot, right? So these constantly change just like everything else, but an interesting snapshot as it will be. So starting from the left, right, Gartner is predicting that you'll have 46% adoption of containers running in some type of production by 2018. Now that's actually a pretty liberal estimate, I guess I would say. However, just kind of as a benchmark, I just came back from a 2-day conference on DevOps. So they have a conference called DevOps Days. And surprising to me, there were a number of large enterprise companies that have actually already began deploying mostly their internal applications in a production environment. And just to name a few, and of course this is in Minneapolis, that's where I'm based out of, a Minneapolis-based conference, but to rattle off some names, Best Buy, Cargill, Wells Fargo, United Health and Optum, largest healthcare provider in the U.S. So these are companies that, again, have already taken that initiative and that step towards containerization, but furthermore have actually, again, begun deploying production applications. Then if we look at the one in the middle, right, this kind of now takes that software-defined storage market, breaks it down specific more towards really containers. So that $2.7 billion is to address what is the actual market size of storage in support of containerized applications. So again, a pretty sizable market if you consider that containers really just came on the scene legitimately a couple years ago. So not to argue with anyone that they haven't been around, that the concept and model of containers haven't been around for well over a decade. They really haven't taken off until the last couple of years. And then again, the last bubble on the right just basically shows a compounded annual growth. So again, a very strong number showing the expected quick adoption and deployment of containers. And again, that refers to storage. So all of this, of course, really is centered around storage for containers. And then I think the last thing, again, I just want to touch on is that quote there below those circles, which is, the number of DevOps adopters, right, that are looking to invest in containers or some type of container orchestration in the next 12 months. And this was taken from an IDC research that was done just in March of this year. That very much, again, this all coincides with everything that I was hearing at this DevOps conference this week, as well as the other conferences that I've attended myself this year, whether it is Amazon reInvent, in which containers and containerization and microservices and DevOps were very hot topics to DockerCon Zone Conference, which is kind of one of the, I'll say, elite container conferences that exist. So all of this helps to reinforce the interest, excitement, and kind of exponential adoption that is happening within the container market. So now if we get specific towards storage services for containers, what you see here shouldn't be much of a surprise. In fact, again, I would argue most, if not all, of these services are equivalent to what would be expected for virtual machines, or really even for bare metal servers, applications running on bare metal servers and applications running in virtual machines. So again, for those that are newer to containers, containers are just a different deployment mechanism, a different infrastructure in comparison to virtual machines or bare metal servers. So without going into each of these, again, I think just the takeaway is the enterprise storage services that have been needed still are needed. The containerization of applications doesn't really change the game. What it does do is it calls out the need for maybe some more advancement in some of these areas, such as supporting scale. So where, you know, a typical virtual machine environment could be hundreds to thousands, with containers, you increase that density typically by 10x. So now you're talking thousands to tens of thousands of containers or container services. Another one would be around quality of service. That's always been, you know, kind of the bane of the existence of running multiple virtual machines on a physical server. Is it's great to increase and optimize the utilization, but in doing so, you oftentimes run into contention or some performance impact of one virtual machine application starving another on the same physical node. So think of that gets exacerbated again with having not just, you know, 10 or so virtual machines, but hundreds of containers all running on the same physical node. So I'm going to pause here for a second, Alex, just to make sure if any questions may have come in. I think I see there's one. Not sure if it's something that I need to address, but I'll pause for a second. Okay, enterprise. Well, this was relating back to a previous slide. So the question was enterprise server SAN versus traditional. So that was more of a category that the company that did this, Wikibon, is the one that put together that chart, so that just how they characterized and classified. So the enterprise server SAN, basically, I think, if I remember correctly, is kind of more of some of the newer SANs where you would include also like all flash arrays versus, again, much more traditional SAN environments that were mainly disk-based, if I remember correctly.
Apologies there, I got caught on mute. Do apologize.
Not a problem. Not a problem. It's all good. So then one of the things that we want to tease out here in today's discussion is some of these gaps that exist in the container storage ecosystem. So as Alex mentioned earlier, storage persistence obviously is one of these gaps, but there are multiple gaps. So if we kind of look at how the container ecosystem with respect to storage is evolving, it's basically evolving where there are many startups that are either already in the space or starting to get into this space. It's a very active community within the container ecosystem. So you have persistence. So what does that mean? So basically the idea of containers, as I mentioned briefly earlier, being very portable. So you can move them from one node to another, whether it's a physical node, it could be one virtual machine on one node to another virtual machine on a different node or within the same. So they're very, very portable and very easy to move back and forth. Because of that, you need to ensure for certain application types that the data supporting that application is persisted as those container services move across these nodes. The orchestration tools, and again, for those that are more familiar, there are different orchestration tools, such as Docker Swarm or Kubernetes or Mesos. They do the storage persistence to an extent, but again, depending on the application, most likely there's going to need to be additional storage services that are provided by a vendor, by some third-party vendor within the storage ecosystem. In terms of performance and resiliency, again, as I kind of touched on before, what's often referred to as noisy neighbor problem or potential performance impact of one application or service to another residing on the same physical node gets exacerbated. So being able to provide guaranteed performance or guaranteed, often is referred to as service level agreements, is very critical for containerized applications. And again, that is not effectively addressed by the different orchestration tools. They have some level of performance definition, but again, it's often not to the extent that the application needs. Referred to complexity, so as many of you can imagine, in any storage environment, complexity can grow very fast, very rapidly. So having, very simplified operations for your containerized environment is critical. And again, this is something where there are some capabilities that are provided by the orchestration tools, but oftentimes these tools are, so Docker, for example, does have a graphical user interface as well as the command line, but Kubernetes, as another example of an orchestration engine, is all command line. So for those that are comfortable with that, that's great. For those that are or would rather have a GUI type of application, if you will, to manage and monitor their container environment, that's where these storage vendors are coming into play. They're providing their own pane of glass to manage the storage in that container environment. And then finally, legacy applications. Basically being able to take advantage of all the benefits that containers provide for traditional monolithic legacy applications. And just kind of as an aside, but relating to this, at the recent DockerCon conference, the big theme this year was modernizing legacy applications. So the idea is that simply by taking a legacy application, and I'll just pick on Oracle again, Oracle DB, and putting that entire application into a container has some inherent benefits just by doing that. And just one, as an example, in efforts of time, would be the portability of moving that Oracle DB application around. So by containerizing it, it now includes everything that's needed to run on different platforms or OSs. So you could easily now take and migrate that Oracle application from Red Hat Linux, for example, to Ubuntu. Or now, with Microsoft supporting running Linux native in Windows containers, you could take it from running in Linux containers to Windows containers. So just by doing that containerization of the legacy app, you get some real interesting and beneficial attributes by doing that. And then if we talk about, what's the difference? So stateful versus stateless. So again, for those that are very familiar with containers and microservices, containers often get equated to stateless. And that's because, again, they often are created or built and torn down within seconds. So because of that concept, again, they're often alluded to as stateless. However, what we find is that there are many applications that are stateful that are beneficial to be run in a container or in a containerized environment. And again, databases happen to be the most often cited application. So whether it's Oracle, MySQL, others, right, NoSQL, et cetera, those are applications that require some level of state and therefore require persistent storage. So what you see here, right, there's some quotes, and I'm not going to read off each of the quotes, but I would say what's more interesting is the chart to the right, which basically highlights, what are some of the important capabilities of a orchestration engine, and being able to support persistent storage, right, being third in that list. You can see that even though containers often get associated with being stateless, when you actually ask the end user, they recognize the need to have, or that their applications do actually have state, or some of their applications have state, and therefore do require that storage persistence. And what I thought would be interesting is this is a just kind of a caption from the Container World Conference from 2017. So that was held a few months back. And what you see is, right, they're trying to highlight all of the areas within the overall container ecosystem that need to be addressed. And of course, right, you see persistent storage right there, top left. So here we are, again, 2017. They've been out for a while. Persistent storage still is a key area that's needed to be effectively addressed by the ecosystem. Again, it's not being addressed to the extent it needs to by these orchestration engines. And so it does need to be addressed in the ecosystem. And again, I would expect that that's going to continue. Don't expect that to go away. And it probably will be either as important, if not more important, as users start to decide to containerize more and more of their applications, right? Whether it's legacy applications or in developing new applications, I think it's going to become that much more important. Storage always is a critical asset, right, for every company. So, and then I think if we look at, again, diving just a little bit more deep, once again, into storage persistence, really we've kind of broken it into four kind of key categories. So the data availability, so again, ensuring that, as I mentioned earlier, as those container services move around from one virtual machine or physical node to another, that the data associated with those services is not only persistent, but as part of that, available, right? So highly available. Again, and this is to support these applications being run in a production environment. You can't afford the data to get either lost or be inaccessible, which basically leads to the next, which is around data accessibility. So with containers, one of the other benefits, as I mentioned, portability and being able to run on different OSs, for example, containers are also very attractive in the sense that you can run them on premises, you can run them in a public cloud, or you could run a hybrid approach. And they're very easy to move from one type of environment or platform to another. So basically the idea is you can run containers anywhere. And again, because of that, you really need to ensure that you have that storage persistence and you have that accessibility, because as you can imagine, if you were to move your application from on-premises to the public cloud and you don't have that storage persistence, again, you could incur data loss, or your application could shut down, whichever is worse, I'm not sure, but neither one's good, obviously. In terms of deployment cycles, basically, again, containers just help to accelerate deployment cycles. So, again, as I mentioned, they're super fast to build or stand up and tear down. And because of that, what's interesting is end users are also deploying containers or deploying applications in containers for things like making it easier to apply security patches, right, or OS upgrades. So all of these things lend themselves because of the fact of how easy containers are to deploy and tear down. And then finally, storage costs, right, with containers. Again, similar to virtual machines, the idea of abstracting them from the physical node or physical server means you're not necessarily tied to, some vendor lock-in. So you're able to take advantage of more commoditized type of environments or servers, and as well as the cloud, as I mentioned. So basically, again, keeping that in mind, if they were moving between different server types, which is another benefit of containers, is you could easily move those services or the applications within a container from, let's say, an HP server to a Dell. Again, you have to maintain that storage persistence. It's just critical, and containers just exacerbate the need for that basically in all cases. And then I think how I am going to end my part of the discussion today is just to give also the viewers some examples from Docker. So for those that aren't familiar, Docker happens to kind of be the vendor that gets the most hype, and to their credit, for really simplifying the adoption and use of containers within an environment. And basically, they've kind of list out, three different types of examples. So you have a Docker registry where you can store your container images and then persist those images. You've got a Docker graph, which basically would be also a different way of storing the container images. And then you've got your kind of traditional concept of a Docker volume. And with a Docker volume, that's probably the easiest to understand, I guess, if you will, where basically the application's data gets stored and persisted in a Docker volume, and then that volume gets associated, let's say, with one or more application services. So that's kind of how Docker presents storage. Again, as you can see, that's fairly simplistic in a way. Hence, as was mentioned earlier, the need for the container ecosystem to really provide those additional advanced storage services, persistent storage being one, and a critical one at that. So with that, I will pause or stop, and then, Alex, I don't know if there was any other questions, or we will then turn it over.
There is, but in the interest of time, I'm just going to introduce Arthur, who's going to talk about persistent memory for containers. Thank you, Chad. Arthur, over to you.
Thank you, Alex. All right, so hello, everyone. The first slide I wanted to show here is a highlight or overview of the memory storage hierarchy. This gives you an idea from the hardware perspective or the server perspective where memory and storage fit in. So on the right, on the pyramid, you see the CPU on the top and then storage on the bottom of that. So typically, NAND or rotating storage is slower, it's block addressable, and there's I/O latencies associated with that. As you move closer to the CPU, it becomes faster with DRAM memory, byte level access, very high speed. So the idea is to create this level of persistence and getting closer to the CPU. So hence all the technology development activity going on in the industry today to create persistent types of storage and persistent types of memory. If you look on the left, you can see how getting to the DRAM speeds today would give you approximately 3 orders of magnitude performance increase by moving in that direction. So I'll talk a little bit more about that, but really these data-intensive applications need that persistence, as Chad talked about, and let's talk a little bit more about that. So here is a chart showing an NVDIMM-Enabled Ecosystem, and I'll give a definition of the NVDIMM in just a moment here. So if we start on the bottom, when we have NVDIMMs-N type plugged into a server, they are recognized through the SPD as persistent. So the BIOS and the memory has to be enabled to recognize NVDIMMs when they're plugged into a server. So once that occurs, you now have a block of persistent memory within main memory. Then it's up to the application and how that is being used. If you go a level up here and look at the OS and the file system, you see different approaches here. On the left, with the page cache and the block-based file system, that's the traditional approach. So there's I/O timings associated with that, and of course it takes longer to access that. And if you move to the right with the direct access, that is the direction the industry is heading today, you're getting from the application direct access to high-speed DRAM memory to the NVDIMM-N plugged into that server. So very high-speed access, persistence. The one in the middle there on the right is DAX. That's a modified version, and that gives you faster access. It's 512 byte level, and then the one in the middle there, the persistent memory-based file systems. Mark will be talking a little bit about that, but that is emerging today. So this gives you a hardware snapshot of how NVDIMM-N types fit into the server application to create this level of persistent memory operating at a DRAM speed. So the three different types of NVDIMMs that have been defined by JEDEC are listed here. So first of all, we have the NVDIMM-N, which is the most common in use today. That is seen by the server as a registered DIMM. It consists of DRAM on one side and flash typically on the other side. It has a controller on it. So the DRAM is accessible by the host, but the flash is not. So during the event of a power outage, the data from the DRAM is transferred to the flash. So the controller on the NVDIMM takes over and manages that data transition process. So the densities associated with NVDIMM-N would be similar to the densities of registered DIMMs today. So 8, 16, 32 gigabyte RDIMMs. If you move down to the NVDIMM-F type, that's not as common today, but there are different variations. It's typically flash-based, up to 1 terabyte. You're accessing at a block level and designed for applications such as putting your in-memory database completely into an NVDIMM-F. And then lastly on the bottom, NVDIMM-P, that is in the works today through JEDEC, and it's essentially a combination of the -N and a -F type. So the media controller allows the type of persistent memory technology on the backside to be transparent. So I've listed there NAND could be used, MRAM, 3D crosspoint, ReRAM, etc. So the host system, it appears transparent to the host system through the media controller, and depending on the type of media that's used, it would be block or byte, and also the access times would depend on that media. So that's a broad overview of the NVDIMMs that are available today or being worked on today, and with NVDIMM-N in particular being the most common. Okay, so the application access to NVDIMMs, as I mentioned, so NVDIMM-N would be byte level access at DRAM speeds. The -P or -F would be block level, and also could be byte level depending on the media type for -P. And again, the most prevalent ones today available are the NVDIMM-N. Let's talk a little bit more about those. So this slide gives you a summary of where they're at. Essentially, JEDEC has been working on them. I'll talk about that in just a moment. SNIA, through the SNIA, the NVDIMM Special Interest Group, we've been giving quite a few presentations and contributing white papers and so forth describing NVDIMMs and their use cases. On the processor side, you have Intel, AMD, and others having native support for the NVDIMM-N. With the OS systems, Linux and Microsoft, they now have native support. So specific drivers or custom specific drivers are not needed anymore, and we'll talk about that as well. And then on the far right, we have systems from Intel, Supermicro, Dell, HPE, and others. So there are a wide variety of systems available today that have native support for the NVDIMM-N type, where you can add persistent memory to a server. And on the very bottom there would be the NVDIMM firmware interface table that provides the physical address space to the operating system of where the NVDIMMs are, and that can be seen by the operating system. So with that, now really the ecosystem is complete, and which has allowed the adoption of these NVDIMM-Ns. So the JEDEC standardization occurred last year in September. The specification was published. Some of the main points are listed here. So with a NVDIMM-N, you have a save pin, so that allows a signal to be asserted In order to initiate a backup, you have a 12-volt pin, which provides the backup energy source, whether it's from the motherboard or tethered to some kind of a backup power module. So that holds up the DRAM long enough for the data to be transferred to the flash. You have an event pin, which if there's an issue or something that occurs, that can be signaled through that event pin. The byte addressable SM bus, which is the standard communication protocol that is followed by the NVDIMM vendors. And then lastly, the SPD, the JEDEC defined SPD registers, which when the NVDIMM is plugged in, it signals to the server that yes, that is an NVDIMM that was plugged in. So with the applications for NVDIMM-N, it's typically write caching, logging, journaling, tiering, checkpoint acceleration. So what you're seeing here would be densities associated with registered DIMMs. So typically it's 1 to 2 NVDIMM-N types per CPU. So that could be 232 gigs per CPU, which allows you to put your logging information into that portion of memory that it has been mapped as persistent, versus an application where you're putting the entire memory database in memory and then calling that persistent. So that would be the differentiating point between NVDIMM-N and other types of NVDIMMs with larger capacities. So they improve performance by, number one, being a byte addressable like DRAM, and that space of persistent memory can be used for any kind of transient data. So there's no I/O, is in the second bullet there. The software overhead is eliminated. So the speed to access this persistent memory is much, much faster and is the same speed as the DRAM. And then the memcache structure is dramatically faster than any solid-state drive or rotating media. And they appear as a DRAM to the system. Some of the challenges, so NVDIMMs have been around for more than 10 years already, and prior to this JEDEC standardization, there were different communication protocols. So the BIOS and the MRC had to be modified to accommodate different iterations of these NVDIMMs. So since that standardization has taken place, that has helped to speed up the adoption. But overall, still, when you qualify an NVDIMM-N, it is dependent on the system. You have to make sure the BIOS, the MRC, the CPU, and the configurations on how they're plugged into the system all have to be checked for specific platforms. And here's a typical use case. So you see 3 tiers of memory here with the persistent memory on the top. So now, based on the application, you can select whether you need the DRAM speed, which is the fastest, and byte addressable, versus the storage tier and the hard drive tier. So now, from that application perspective, it would be dependent on how that data needs to be accessed and how it needs to be saved. And with that, I'll pass it over to Mark.
Thank you. Mark.
Yes. So we're going to talk about how this new paradigm changes the infrastructure. Applications are going to use the persistent memory in different ways. They might start off, for example, using a wrapper kind of to give them the file system and block semantics that they are used to or that their application is already written to. And that will speed things up because now the media is different. You're not talking to NAND, you're not talking to spinning media, you're talking to memory speed media. So that will get you a great increase in performance, but it's not optimal. And to make it optimal, you would need to rewrite your application, and then those applications could optimally use the persistent memory at memory speeds without an intervening I/O wrapper. So SNIA has modeled the new interactions and the programming constructs necessary for this in the NVDIMM programming model. And this allows you to have either disks or persistent memory for your application. If you mount a file system, for example, with a traditional disk behind it, you have the file system semantics. You might have a file system cache and RAM, and you can memory map applications to memory. But eventually, you're going to want to commit those off to the disk, right? With persistent memory, you can also use file I/O to a file system and a driver that understands persistent memory, or you can directly load and store from the CPU straight into persistent memory, and we'll talk about how that affects your application. So the programming model talks about two different ways of using non-volatile persistent memory. One, as I said, appears as a disk drive or a file system. So you can use your typical block-oriented storage. And then you can also treat it like memory itself, and that appears as memory to the applications. Applications store directly in a byte addressable memory, and there's no I/O or even DMA necessary. So persistent memory really refers to this memory-like non-volatile memory. So we just released a new version of the NVDIMM programming model, version 1.2, last month. The link to it is there. Once you get the slides from Alex's pointer, you can then click on that, or you can just Google it. And we added some major new error handling capability, as well as something called optimized flush, which won't flush if you don't need to, and will flush if you do. And even a deep flush, which makes sure that that actually gets out into the persistent media. We can use memory map files for persistent memory. It's an existing abstraction that works, as I said, with hard drives today, just using a file system cache. But that still limits the scope of the application reinvention. It's still not optimal, but there are open source implementations available of memory map files. The programming model itself is not an API. It is a common way of thinking about how an application interacts with persistent memory. So we have attributes, we have actions, we have use cases, and then it's up to the implementations to map those to its own APIs. So you'll see a different API on Windows than you will on Linux, but your application then has the ability to use these features that we've defined. So in the programming model itself, there's 4 modes. We have a block mode innovation with atomics, access hints, and NVDIMM-oriented operations. So from the user point of view, you can use the NVDIMM.file model, or you can use the NVDIMM.block model. That's kernel protected, and that can work with either disk drives or media, disk-like media, like NVDIMMs. And then there's the emerging NVDIMM technologies, which gets you performance. And there we have an NVDIMM.PM, which means persistent memory, file. We have NVDIMM-PM volume, and then, of course, you can use it just like memory and persistent memory access directly. So graphically, this sort of looks like this. On the left, you have block-aware applications that can go into persistent memory block mode extensions to use a persistent memory block device. And then on the file-based applications, the file system itself would use that same block device to access it. And these are the 2 modes here, the NVDIMM block mode and the NVDIMM.file mode. And then the NVDIMM.PM.volume mode is a PM-aware app now is using PM-aware file systems and PM-capable drivers to do their block and file access. And again, they can use straight memory direct to the PM device as well. So the NVDIMM.PMNet file surfaces persistent memory to the application, and we're considering the requirements to the model with additional libraries, and then some may even evolve into language extensions. And what we mean by this is the language could be supporting persistent objects or persistent structures in the language itself. And as far as libraries are concerned, the critical thing there is to support sort of a persistent memory allocation and persistent memory free operations so that the application can treat persistent memory different than it can the regular volatile memory. So what changes, right? Well, first, the operating system needs to change. That's mainly what we've been talking about here. And in specific file systems, they need to make those changes for persistent memory aware memory map files. Memory management software in the operating system needs to be aware of persistent memory. Hypervisors would like to take that persistent memory and allocate it to different guests. And so then they have to coordinate with those guests' use of persistent memory. Do you want the persistent memory to stick around after your guest goes away? Or maybe you move it off to some other kind of shared media instead so that that guest can instantiate somewhere else. And then, as the subject of this webcast, in containers, we want those user space libraries to support persistent memory for container applications. We still want to support legacy interfaces with persistent memory aware implementations of file systems and block drivers. And then we need to worry about securing application data in this multi-tenant persistent memory environment. So you've got your standard file API up here in this pink layer here. And then we've got what we just added in 1.2, this optimized flush. And that flush will even flush it out to a mirrored piece of persistent memory over a network interface. So you've got the local file system, you've got the remote file system, accessible via something like a network file system client. But that gives you not only reliable storage of your data, but also available storage of your data, because if something happens to the primary system, the secondary system has that persistent data in its own NVDIMM, for example. So what do you have to change in your application if you want optimal use of persistent memory, right? They don't have to change anything, and they can still use the faster speeds of persistent memory with these operating system drivers wrapping the persistent memory. But we really want to start to move these applications to be aware of the NVDIMM programming model semantics, right? And so that's the library support with the PM-alloc. It's compiler support for the persistent objects, and it's high availability support for making sure that the data you put in persistent memory is available despite system failure. So there are some changes that have been put into the Linux kernel. NVDIMM-OS support is now available in 4.4 and beyond. So it's actually doable now. You can buy NVDIMMs off the shelf. You can get the latest Linux kernel and use it. You can use that Linux kernel with Kubernetes, with Docker, etc. And so that allows support for the applications as well as the infrastructure that you're using to host your containers. And back to Arthur for some slides on Windows support.
Thank you, Mark. So in addition to Linux, Microsoft also has, go one more slide here. Do you want to say anything on that slide, Mark?
No, I mean, that's just for people when they download the slides, you can find the open source contributions.
Okay. So in addition to Linux, Windows also has native NVDIMM-N OS support, and that happened last year. That can be in block mode or direct access mode. Some of the data that's shown here, there's another example on the next slide, but shows you the IOPS and the latency benefits of using NVDIMM-N in either block or direct access mode. So this next slide is an example from Microsoft, and it's running on an HPE server. It's an online transaction processing workload. So you're doing logging in memory. So if you look on this chart, the far right, that red line would be a hard drive, and the transactions committed to a hard drive. The speed and the latency is on the bottom, and the scale on the bottom is in its orders of magnitude. So it's a logarithmic scale, and the speeds on the left are faster and on the right are slower. So you're comparing an SSD versus a hard drive. The SSD is a blue line in the middle. And then on the very far left, you're plugging in an NVDIMM-N. The blue line is with an SSD and an NVDIMM-N. And then the line next to that would be an NVDIMM plugged in with a traditional rotating drive. So what you're seeing is very low latencies. So you're committing transactions to memory, persistent memory, via use of the NVDIMM-N combined with the SSD or rotating drive. And those spikes, they are also indicating the cache, the waiting times. So there's a video online. It was done by Lindsay Allen and Tobias Klima from Microsoft. They do a very good job explaining this. I encourage people to take a look at that. But it just gives a good example of the benefits of being able to plug in these NVDIMM-Ns into a server and getting the immediate performance benefits of low latency, high speed access to a persistent section of memory.
Thank you, Arthur. Thank you, Mark, and thank you, Chad. My apologies, by the way. I see the number of people are complaining about the quality of the sound and that the audio was dropping out. And secondly, that this presentation required flash. Yes, I know it's a dead technology. Yeah, we need to evaluate that. But my apologies if you had any trouble today because of either the audio or the flash. However, just to summarize, there's a Flash Memory Summit taking place August 7 through 10 at the Santa Clara Convention Center in California. And we're going to be discussing a lot more about persistent memory and NVDIMMs. There are 3 sessions there. We're talking about an overview of persistent memory to start with. Then there are 2 forums, persistent memory convergence of storage and memory on Wednesday. And then on the Thursday, there's a forum, powerful persistent memory arrives in a familiar form. So we're talking quite extensively at the Flash Memory Summit about some of these new persistent memory technologies. The presentation today is available now. You can actually go out to our link there on SNIA.org, forum, CSI, knowledge, webcast, and you can pick up a copy of this presentation. That may also encourage you to look a bit more detail at the slides. Some of the detail doesn't come through in this particular platform that we use for presentations, but the slides are in high resolution and you'll get all the details on the copy of the slides. We're also going to be doing a Q&A from the webcast. So any outstanding questions that haven't been answered today, we'll be answering and putting up on our blog at sniacloud.com. And you can also follow us on Twitter, and there are 2 Twitter handles, SNIA Cloud for the Cloud Storage Initiative and SNIA Solid State. Sorry, I'm gobbling here. SNIA Solid State for the Solid State Initiative. On the way out, I'd be very grateful if you rate this webcast. We value your feedback. I do understand we've had a few technology problems for which I apologize. But if you'd rate the content and the quality of the kind of information we're trying to deliver, that would be most helpful. In the meanwhile, thank you very much for attending today. Thank you for coming along and listening to our experts. And thank you, Chad. Thank you, Arthur. And thank you, Mark, for providing such an entertaining and informative presentation for us. Thank you very much, everyone. Bye now.